No area of physics causes more confusion, not just among the general public, but also among physicists, than quantum mechanics. On the one hand, it's the source of New Age mythology and has enabled hucksters to peddle new self-help cures. On the other, for the philosophically inclined, it has provided some illusory hope of free will in an otherwise deterministic universe. Of the aspects of quantum mechanics that confuse and dismay observers, perhaps nothing approaches the property called entanglement. Einstein, who never really accepted entanglement's existence, called it derisively spooky action at a distance. Unfortunately for Einstein, entanglement, spooky or not, is apparently real, as researchers in the Netherlands demonstrated last week, just in time for Halloween. In doing so, the researchers affirmed once again that quantum mechanics, as strange as it may seem, works in every way we can test it. To understand just how spooky entanglement really is, it helps to step back and think about what happens to sensible, classical objects when you separate them. Classical objects are large enough or interact strongly enough with their environments for quantum mechanical effects to wash out. Imagine that I have a detonator and a bomb. If I separate them across the street from each other and activate the detonator, it can trigger the bomb only by sending a signal at the speed of light or slower. Only after the bomb receives a signal will it detonate. Quantum theory, however, suggests that objects which have been carefully prepared together and placed into a combined quantum state can, even when separated across the galaxy, remain entangled, as long as neither has any significant interaction with other objects to break the entanglement. If I perform a measurement on one of two entangled objects, the state of the other object will be instantaneously affected, no matter how far apart the two objects are. In itself, this may not seem that spooky. After all, if I separate two identical twins across the galaxy and then observe that one twin has red hair, I have instantaneously determined that the other twin has red hair too. The real spookiness comes in only when you consider what a measurement in quantum mechanics really involves. Imagine a pair of electrons. Electrons behave as though they are spinning. Moreover, because they carry an electric charge, they act like small magnets, which means that using electromagnetic radiation, it's possible to manipulate their spins. One pair of electrons, for example, can be set up so that their spins point in opposite directions along the same axis. We can say that such electrons are anti-aligned. Now suppose that later I try to measure the axis about which one of the electrons is spinning. If it's spinning in one direction around that axis, it acts like a magnet with its north pole pointing in a direction we can call up. If it's spinning in the other direction, then its north pole would point down. Because the electrons are anti-aligned, if I discover that one is pointing up, then I know that its partner must be pointing down. There's a catch, however. Quantum mechanics says that the actual spin direction of either electron is not determined in advance of the measurement. The only thing that's for sure is that the spins are anti-aligned. Even stranger, until they have been measured, both electrons are actually spinning up and down at the same time. Their measured state is probabilistic. All that can be said is that there's a 50-50 probability that once the electron is measured, it will be fixed in a state of spinning up or down. Because the two electrons are in a single quantum state, because they are entangled, the moment I measure the spin of one electron, I fix the direction of spin of the other electron. It's as though by flipping one coin and coming up heads, I force another coin to come up tails. As long as the two electrons remain entangled, then this link endures, even if they are separated across the galaxy. If I measure one electron in my lab, the second electron is affected by the measurement of the first electron with no time delay, instantaneously, even though a signal traveling at the speed of light would take millennia to cross the distance between them. That instantaneous link is the spooky action at a distance of which Einstein was so skeptical. In his day, of course, no one had actually observed entanglement. It was just a prediction of quantum theory. In 1935, Einstein, along with two collaborators, Boris Podolsky and Nathan Rosen, wrote a famous paper arguing that entanglement was so crazy that if quantum mechanics predicted it, the whole system had to be flawed. No system that made such predictions could possibly describe the universe accurately. Einstein and his collaborators were thinking classically, imagining that the electrons were separate objects when separated. But quantum mechanically, the two electrons are part of a single quantum state, no matter how far apart they are. They are not independent, well-separated objects. Indeed, quantum mechanics tells us that until we measure the position of either electron, we cannot say for certain where it is located. It can be, in some sense, everywhere at once. Over the years, some physicists have channeled Einstein's skepticism. They have proposed that there is some hidden classical mechanism we don't know about, which is somehow fixing the results so as to create the appearance of entanglement. Perhaps, for example, the laboratory setup is somehow predetermining the spin directions of the electrons before they are separated. This conjecture has presented physicists with an impasse. How could we ever know that some hidden mechanism wasn't at work? In 1964, a physicist named John Bell found a way around it. He wrote a beautiful paper demonstrating that if an entanglement experiment worked reliably, a specific set of measurements could be made on the particles which produced a quantitative result that couldn't be explained by any classical mechanism, which might predetermine the spins before they were measured. Over the past half-century, many groups have used Bell's theorem in trying to affirm that quantum mechanical entanglement is real. All the while, however, skeptics have pointed out in each experiment there may have been subtle loopholes. It's been possible, for example, that systems which were supposed to be separated may have actually been coupled in hidden ways. Last week, a team of researchers led by a physicist named Ben Henson at Delft University of Technology in the Netherlands reported the results of an experiment designed to lay these concerns to rest. They performed simultaneous measurements on a pair of entangled electrons separated by 1.3 kilometers, far enough that no signal, even one traveling at the speed of light, could get from one detector to the other in time to interfere with their measurements. They also devised a way of independently checking that the electrons being measured were in fact entangled. Both these aspects of their experiments are significant and novel. They remove key loopholes which skeptics had argued might bias previous experiments. Needless to say, the new results agreed precisely with both the predictions of quantum theory and of Bell's theorem. Entanglement now appears to be an empirically closed case, at least until someone can convincingly argue that there is some loophole not ruled out by this experiment, which some physicists have already begun to do. If that happens, other researchers will inevitably attempt to produce an even better experiment, in which Bell's theorem will be satisfied while the new loophole is ruled out. The cycle will repeat until there are no loopholes left, or until those that do remain seem so implausible that it isn't worth the effort to explore them. I say this with confidence because even though these direct measurements of quantum spookiness are important to perform, we can already be sure that quantum mechanics is the correct description of the world at the smallest, most fundamental scales. In fact, we test that assumption every day. Most of our modern technology depends on it. The semiconductor transistors that govern the behavior of our cell phones, our computers, our cars, and many other electronic devices are based on quantum mechanical principles associated with the electronics that drive their computing capability. Those principles hinge indirectly on the spookiness being measured explicitly in the Delft experiment. So, spooky or not, our lives in the modern world rely on quantum mechanics in many ways. Entanglement is so spooky that it's tempting when thinking about it to draw nonsensical conclusions. Deepak Chopra, for example, keeps implying that quantum mechanics means that objective reality doesn't exist apart from our conscious experience. The truth, however, is that consciousness is irrelevant to the act of measurement, which can be done by machines or even by single photons. If consciousness matters, then the inner thoughts of the experimenter who operates the machines would also have to be reported when we write up the results of our experiments. We'd need to know whether they were daydreaming about sex, for example. We don't. The machines can record data and print it out whether or not a person is in the room. And those printouts, which behave classically, don't change when the humans come back. Similarly, last week, the Pulitzer Prize-winning writer Marilynne Robinson published an essay in which she challenges the nature and relevance of modern science. The essay argued that entanglement raises fundamental questions about time and space, and therefore about causality. She went on to say that this called into question the ability of science to explain reality as a whole. It's easy to understand how Robinson arrived at this incorrect idea. When a measurement of one electron here can instantaneously affect the measurement of another electron on the opposite side of the universe, faster than the speed of light, it does seem as though causality has been thrown out the window. But the lessons of quantum mechanics aren't that simple. The truth is that nature contains a cosmic catch-22. Consider our two experimenters, one located here on Earth and the other stationed at the edge of the Milky Way. Separately, they measure the spins of their entangled electrons. Nothing about what they measure will point to a measurement going on thousands of light years away. Each of them will measure their electrons spinning up 50% of the time and down 50% of the time. Nothing will suggest that the spins of their electrons are correlated with electrons anywhere else. The only way they can realize this is if they communicate with one another. But that communication can happen at its very fastest at the speed of light. Entanglement may be instantaneous, but it produces no signals that can be detected instantaneously. Its detection still follows the ordinary laws of cause and effect. Quantum mechanics reveals that nature is indeed spooky at its smallest scales. If we are careful, we can detect that spookiness. But happily, its presence doesn't mean that all bets are off. The fundamental laws that govern the universe don't disappear in a quantum haze. The strangest thing about entanglement may be that it fits so neatly into our broader understanding of the universe. Thanks for watching.
Every cell of each plant and animal contains genetic information coded onto the DNA molecules. The model